Hi there, in this video we'll discuss sections 22.5 and 22.6. We'll set up a confidence interval and a hypothesis test for the difference between two means. Comparing two means is just like comparing two proportions. So the steps we discuss will mirror the steps we had before for comparing two proportions. We'll see that the sampling distribution for the difference between two means, provided we have independent groups, can be modeled closely by a student's t-model with a number of degrees of freedom found with a special formula. Let's start with the assumptions and conditions. For independence, this is the same as for comparing two proportions. We need independent values in each group and independence between the groups. So primarily what we'll be checking here is randomization. We'll view randomization as evidence of independence. In addition, we must assume that the underlying populations are each normally distributed. So we check the nearly normal condition. The data for each group come from a distribution that is unimodal and symmetric. So let's look at how we set up the confidence interval. This is also referred to as a two-sample t-interval, and it looks like this. We take the observed difference in the sample means, y1 bar minus y2 bar, and add and subtract this critical value t star times the standard error of y1 bar minus y2 bar. Now this critical value t star depends on the confidence level we specify, and it comes from the student's t-model instead of the normal model we used before when working with two proportions. It turns out the sampling model isn't exactly the student's t-model, it's just something close to that. But if we adjust the degrees of freedom using a special formula, the sampling model is so close to the student's t-model that we can't really tell the difference. So let me demonstrate how we can use a calculator to find this adjusted degrees of freedom. Suppose the first sample size is 654 and the second sample size is 813. In fact, these numbers come from the project you'll look at for this section. Suppose the sample standard deviation for group 1 is 1.777 and the sample standard deviation for group 2 is 1.760. Then when I hit compute degrees of freedom, it reports the degrees of freedom is 1,392.7564. So we'll typically just use technology like this to compute the adjusted degrees of freedom. Let's talk a little bit more about how we determine the standard error. If you recall, for independent random variables, the variance of their difference is equal to the sum of the variances. So we're going to again use this result to determine the standard deviation of the difference between the two independent sample means. The standard deviation of y1 bar minus y2 bar is equal to the square root of the variance of y1 bar plus the variance of y2 bar. And so that looks like this. It's the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Now, sigma 1 is the true standard deviation for population 1. N1 is the sample size for group 1. Sigma 2 is the true standard deviation for population 2, and N2 is the sample size for group 2. As before, or as always, we don't know the true standard deviations of the two groups, sigma 1 and sigma 2, so we'll use what we do know. and that is the sample standard deviations S1 and S2. So the standard error of y1 bar minus y2 bar is equal to the square root of S1 squared over N1 plus S2 squared over N2. So notice all I've done is replace sigma 1 with S1 and sigma 2 with S2 to get the standard error. And so that's how you determine the standard error. We talked a little bit about using the calculator to find the degrees of freedom we need to determine our critical value T star. And so this is how we construct the confidence interval. The corresponding hypothesis test is called a two-sample t-test, and you'll get some practice working with this on the project for this section. So I'll see you next time.